Okay, have you ever made a change to something and then wondered, did that actually do anything? Or is what I'm seeing just, a random fluke? Well, today we're diving into a powerful statistical tool called the one sample t-test that helps us solve exactly these kinds of mysteries. Let's get into it. So here's our case file. A university rolled out this brand new online statistics tutorial. They spent time, they spent money, but did it work? Did it actually help students get better grades? It seems like a simple question, but to get a real, trustworthy answer, we've got to think like statistical detectives. All right, first things first. Every good investigation starts with laying out the facts. So let's look at the evidence we have so far. So, we've got the scores from a random group of 12 students who use this new tutorial. And, well, you can see they're kind of all over the map, right? Some did great, some not so much. Just staring at this list of numbers doesn't really give us a clear answer. Now here's our baseline, our point of comparison. For years, without this tutorial, the average score on this exam was a solid 28. This is the established fact we're going to measure against. And when we crunch the numbers for our 12 students who did use the tutorial, their average comes out to 32.33. Hey, at a glance, that looks pretty good. That's a noticeable jump. And here it is. This is the million-dollar question. Is that 4.33-point bump a real effect from the tutorial? Or did we just happen to pick a slightly smarter group of students this time around? Could this all just be random luck? How can we possibly know for sure? Well, this is where our hero tool comes into the story. To solve this mystery, we need the one sample t-test. It is designed for exactly this kind of situation. So what is it? Put simply, a t-test lets us compare the average from our small sample, our 12 students, to that known, established value, which in our case is the old average of 28. Its whole job is to tell us if the difference we're seeing is big enough to be considered statistically meaningful. And this is so cool because it's not just for student exams. Companies use this for quality control on their products. Medical researchers use it to see if a new drug actually works. Social scientists use it to compare a specific group's opinions to the general population's. It's an incredibly useful tool for anyone who needs to make decisions based on data. Okay, so before we can actually get our answer, we have to frame our question in the proper language of statistics. This means we need to set up two competing ideas, two opposing possibilities that the test is going to decide between. And this right here is the heart of hypothesis testing. First, you've got the null hypothesis, or H0. This is kind of the default boring assumption. Nothing interesting happened. The tutorial did nothing. The average is still 28. Then you have the alternative hypothesis. This is what we actually suspect is true. The tutorial did have an effect, and the average score isn't 28 anymore. Our whole goal is to see if we have enough evidence to throw out that boring null hypothesis. We also have to set a rule for making our decision. This is our significance level, and we'll use the standard 5%. Think of it as our beyond a reasonable doubt line in the sand. If the math tells us that the probability of our result happening by pure chance is less than 5%, we're going to say, okay, something real is going on here. All right, the stage is set. We've got our hypotheses, we've got our rule. Now it's time to actually dig into the data and find the clues that are going to lead us to an answer. I absolutely love this analogy. The entire t-test really boils down to this one number called the t-value. It's basically a signal-to-noise ratio. The signal is the difference we saw, that 4.33-point jump. The noise is just the natural random variation in student scores. A big t-value means our signal is loud and clear, and it's punching through all that background noise. Now, the best part? We don't have to break out the old calculator and do some crazy formula by hand. Statistical software does all the heavy lifting for us. We just need to feed it our key ingredients, our sample size of 12, our mean of 32.33, and the standard deviation, which is just a fancy number for measuring that noise or spread in the scores. And when we plug all that in, the software gives us this, a t-value of 2.75. This is it. This is the central piece of evidence in our whole investigation. It tells us our signal is 2.75 times stronger than the noise. But the question is that strong enough? So now we get to the climax of our story. We've got our key clue, that t-value of 2.75. It's time to interpret what it means and deliver the final verdict on this online tutorial.
A t-value of 2.75 by itself doesn't really mean much to us, does it? What we really need to know is the probability behind it. In other words, what are the odds of getting a signal this strong if the tutorial really did nothing at all? To figure that out, we need to translate our t-value into something called a p-value.
And here it is. The p-value that corresponds to our t-value is 0.02. This little number is the key that unlocks the entire mystery. So let's translate that. What this means is if the tutorial had absolutely zero effect, there would only be a tiny 2% chance of seeing a score increase this big just by random luck. A 2% chance? That's pretty unlikely, isn't it?
Now for the final check. We just compare our p-value to that line in the sand we drew earlier. Our p-value is 0.02. Our significance level was 0.05. Since 0.02 is smaller than 0.05, we have cleared the bar. We can officially say our result is statistically significant. We can reject that boring null hypothesis.
But wait, there's more. There's actually another piece of evidence we can look at to confirm our finding. It's called a confidence interval. The software tells us that we can be 95% confident that the true score increase from the tutorial is somewhere between about 0.86 points and 7.81 points. And the rule for interpreting this is super simple. If this range included the number 0, it would mean that no effect is a plausible outcome. But look at our range. It's entirely positive. It goes from 0.86 up to 7.81. It does not cross 0, which is another way of confirming, yep, our result is significant. So the verdict is in. We can finally answer that original question with confidence. Based on all the evidence, the university's new online tutorial really did have a positive effect. That improvement we saw in the students' scores, it wasn't just a random fluke. Okay, so we cracked the case for this one university, but beyond this one example, what's the big picture here? Why is this process so important? What's so powerful about the t-test is that it gives us a clear, repeatable method to get past just our gut feelings. It's a structured way to ask a question, challenge the default assumption that nothing has changed, and then use the power of probability to decide if what we're seeing is a real signal or if it's just noise. Ultimately, tools like the one-sample t-test help us cut through a world that's filled with data and noise to find real, credible answers. It gives us a way to test our ideas rigorously, and it turns a simple question into a confident conclusion. So take a second and think about it. What question in your work, or even in your life, could you finally get an answer to? With this tool, you now have a way to find out.